Bernoulli sequences. So we've talked about discrete values. We've talked about continuous. We've talked about how to find the means, the standard deviations via the variances, and I've also described to you how you would find the probability for each of those. So for continuous, we integrate between the two values, whereas for discrete, it's actually given already what the probability is going to be. Sometimes you just have to do like it'll give you the probability of yes is 0.5, what's the probability of no, and it'll be like also 0.5, so 1 minus that. But usually it's kind of like what you did in year 10, kind of common sense as opposed to having to plug in values as it is for your continuous variables. Okay, Bernoulli sequences, number 3 on what we are going to talk about today. So, Bernoulli sequences describes a sequence of repeated trials. And one thing to note is Bernoulli sequences are always success and failure. That is essentially what is going on here. We're talking about a success and a failure. And the probability of success is P. The probability of failure is 1 minus P, because there's only success and failure. And remember that the probability of all outcomes has to add up to 1. So what does that mean? That means that if the probability of success is 0.2, well, that means the probability of failure is 0.8, because there's only 2. Binomial, it's got to add up to 1. Okay, so I have 3 rules here, and I've said that you have to memorize them because you have to memorize these. These are 3 rules, and they're it's one of the little points where you actually can get marks for essentially just writing stuff. So if you memorize these 3 rules, there can be questions on an external exam where it's like write the 3 assumptions, the 3 rules of Bernoulli sequences. Sometimes you might be asked which would be a Bernoulli sequence, and we're going to go into an example that is talking about that in a minute or two, because you could get this a multi-choice. I will note that the first 10 marks of that first paper is going to be multi-choice, and multi-choice can be difficult because if you make a little error, it's so easy to have, to pick, because they'll have the little errors translate to different questions, different options, A, B, C, D. And you might just go, oh, it must be D without checking, and you lose easy marks. Multi-choice is a place where, like, you need to, like, you can achieve easy marks. I would always drop, like, 1 mark even, maybe. I usually aim for 10, but sometimes you lost a mark because sometimes it can be a bit iffy. But this could be an example of a multi-choice question. And yeah, multi-choice, also make sure you write, like you can circle it on the booklet and cross out wrong answers. Make sure you color in the bubbles. At my school, in my year, in general maths, so not methods, there was, a student that didn't fill in the bubbles and and they were already in a poor shape, ended up failing the year because you need, like, if you don't fill in the bubbles, you're missing the simple, familiar, easy marks on the paper that they're ultimately trying to get you to pass with. Fill in the bubbles and just use a lead pencil so you can rub it out. Just do it early on in the exam once you've done it, and then you can come back and change it later. So the 3 rules I do want you to memorize. For me, this is a key learning objective. Need to memorize these 3 Bernoulli sequences. We can only have success and failure, number 1. Number 2, the probability of success, P, is constant for all trials. That's 2. Number 3, the trials are independent. Write these ones down. You need to memorize these 3. Okay, so here's an example, as I said, where we're going to actually test this in an actual scenario. So, which of the following is a Bernoulli sequence? If you're rewatching this, you can pause it, have a go. If not, I'm going to go through them now. So, the only one that I've classified as a Bernoulli sequence is A, B, could be, but, we're not, technically it's not. So, A, we're tossing a fair coin a few times. So, fair coin, that means the probability is the same. It doesn't matter what it's just landed on as to what it will show next time. So the trials are independent, and it's success and failure. It's either tails or heads. So by success and failure, we just mean one outcome or another. If there's just 2 outcomes, or we can classify it as just 2 outcomes, or lump them together so that it's just 2 outcomes, it is success failure, binary, it's going to be a Bernoulli sequence. So A is a Bernoulli sequence. However, when we look at B, so trying to score a goal multiple times, this is unlikely to be independent. And the reason I say that is like if you've scored a goal, it's going to give you confidence, and you're probably going to be more likely to score a goal in the future. Like athletes who start doing well are more likely to then keep on going and do well. Also, the probability is not therefore going to be constant. Like you know, you're going to be tired by the end of it. The chance of scoring a goal might be higher or lower at the end, depending on your level of fatigue versus the goalkeepers. Hence, those last two, so independent trials, not true because if you've scored a lot of goals, you're probably more likely to keep scoring due to the morality, the psychology of that. Number two, also the probability of success is different. It's changing, it's fluctuating due to fatigue and stuff like that, more of this human kind of psychology type thing. So as you can see, as soon as there's a human element to it, unlikely to be a Bernoulli sequence. But then again, like if you had quiz results and they were random, I mean, if they've told you it satisfies the three, I'm happy. Okay, finally, we had selecting people at random from a high school grade and noting their age. This is not success and failure, unless we specified and we said, and noting whether their age was 20 or not 20, but like 12, that would then be success failure. But the way this is worded, selecting people at random and noting their age, uh, sure, probability of their age might be random. However, and trials, sure, probably independent, but there's not success failure here. So C is not a Bernoulli sequence. Okay, a bit more on Bernoulli sequences. So Bernoulli sequences are typically, or they are discrete random variables, and that's because it's success or failure. It's a discrete outcome. It's either going to be success or it's going to be failure. And often we use Bernoulli sequences to kind of like extrapolate some probability questions for some of our discrete variables, as I'm sure you're going to see in your class, and also we're going to go over some. So the outcomes from a Bernoulli trial and sequence can be represented by Bernoulli random variable. We can set it up in a table like this. This is just a nice 2 by 2. Y, we have failure and success, and then the probability that Y or X equals that is defined there. So one take P for failure, P is success. Now, I've defined from memory, there's a couple of key steps for a Bernoulli sequence question. Uh, and these ones are pretty universal, so I reckon this is worth writing down as well. First of all, and I will note more broadly in a more meta sense, if you can write out the steps for answering questions generally, like go through the objectives, what steps are there to answer those generic questions? You can find the objectives by Googling methods 3-4 syllabus, QCEE, and go through that until you find them. What number, if you can write the steps out for each objective, you're going to do really well because you've now got a really nice conceptual understanding. And that's going to make your application oh so much better, right? It's going to really help you differentiate these different types of probability because right now it's difficult because you're like, it's all blending together. However, once you've differentiated them clearly, for example, the typical things for a Bernoulli sequence, you know it's that, and you use that formula from your data booklet that we're going to go over. When you see success, failure, etc., when you see that, you know you've got to go over Bernoulli sequences. Okay, so the steps to answering a Bernoulli sequence question. Number one, identify. Does it meet the three criteria that I just said on the other page? And that's going to tell you you're going to be using the formulas from the um, data book, which we're going to go over. Don't worry. So number two, define one of the outcomes as success, which is X. Then you want to fill in other values from the data booklet, and for example, the probability of X, like what's the value of X between out and because what we're going to be doing essentially is filling in. There's this formula on the data booklet labeled Bernoulli sequences, and you're just going to be filling in the number, the probability, and then working it out. And sometimes we have to do a bit stuff that's a bit more complicated for that, as I will show you. So this is the formula in the stats page. This weird thing here is what I'm going to go over now, because the rest you can just sub in the value of x, the probability that x equals x. So this is kind of talking about like the number. So if we have, so I'm going to explain this in simple terms when you use this formula. Question asks, what is the probability that we're going to have? So we have, you're rolling the dice 6 times. What is the probability that you're going to get? So the probability of success would be 1/6. What is the probability that you're going to roll 2 6s if you roll the dice 6 times? And so what you're going to do is whenever you see a 2 here, you're going to sub in 6 for 6 trials. X would be 2. So we're finding the probability that X, which is the number of that, equals 2. So 2 success outcomes. We define success as getting a 6. Probability would be 1/6. So 1/6 to the power of 2 times 1/6 to the power of 2. And this here is called a combinatorics. I'm going to show you that. Don't worry. It's that. But now we would find, and this formula just allows us to work out what the probability of actually getting that number of sixes would be. That's for your Bernoulli sequences. So you would define, so identify, is it a Bernoulli sequence? Yes. Define one of the outcomes of success. Then you fill in these values. For example, the number of trials n, for example, x, the number we're interested in, and the probability of x as well. Okay, so Bernoulli sequences, combinatorics, you should have learnt this in year 10, but different schools are different. Um, we use this formula, and this isn't given on the data booklet, which is quite frustrating. I know for my calculator, if you just typed in NCR bracket, the N comma R, it'll tell you. But R is the X value, essentially. It's the value of X there that we're looking for. It's like the actual value that we want, right? Whereas N is the total number of trials. And it's just multiplied out the front to this formula, which is kind of annoying. But as you see in questions, you eventually get used to it. The way to think about it for the order is n chose r. And the reason I say that is we can use Pascal's triangle to calculate these combinations tech-free in methods. You're going to have to Google how to do it tech active because I don't know what your calculator is. For me, it was just NCR bracket, whatever, whatever. But just look at a YouTube video. It really does help. Okay, so you have to memorize Pascal's triangle. This is universal for your tech-free questions. And what happens is we've actually got these values here. So you go 1, 1, 1, 1, 1. One's always on the outside, and you go in these different rows. This row would be 0. This row would be 1, 2, 3, 4, 5, etc. N goes down, R goes across. R being the number we're interested in, the X value gives specificity. And what you'll see is when you're drawing this, so have a go at drawing this. 1, 1, 1. This 2, well, I'm not just making this up. This comes because 1 plus 1 is 2. Then we put 1s on the outside. Now, if we go 1 on the outside, 1 plus 2 is 3. 2 plus 1 is 3. 1. Then here, 1's on the outside. Just adding 1 each time because it's like a triangle. 1 plus 3 is 4. And 3 plus 3 is 6. 3 plus 1 is 4. And then we put a 1 on the outside. And we just keep going down and down and down into perpetuity. And you do need to memorize this, or at least how to work it out. For example, if we had like n equals 5, r equals 2, well, we would go down to 1, 2, 3, 4, 5. This would be 1, 2, would be 4. So the value of this thing here would be 4. We would sub in 4 to that equation to then work out the probability that we get that number of successes in that many trials. Okay, cool. Now, there's a couple that you do need to just straight away memorize, unfortunately, and that is that NC0, so when R equals 0 is 1, NC1 equals N, NCN equals 1. So just write those on your formula sheet. If you ever get a question like that, it's nice and easy. You don't have to do Pascal's triangle. You could, of course, do Pascal's triangle. You get the same, but I would just memorize these really quickly as well. But yeah, these ones are to memorize. These are not on your formula sheet. Okay, so this would be an example. It is actually the example I made up just now. So obviously my memory recalled it. So Bernoulli sequences, consider rolling a die 3 times and letting x be the number of threes represented. Well, the probability that x equals 3 is going to be, if we extrapolate it, what are we going to get? I'm just showing the derivation of the formula here. What we would do is, we would let success, which would be t, equal 3. N would be not a 3. We could also let x equal success, so equals 3. And the probability that x equals 3 is 1/6 to the power of 3 of getting TTT. And this is just using like our tree diagrams, something that you learnt back in, year 10. There's different combinations of TTN, etc. And I don't want you to know these. This isn't typical for me. What I want you to know is to know these 3 steps, and then and then apply them. Sub it in to this formula, which you might have to use that for if it's tech free. So this is the different combinatorics we would use. So when x equals 3, we'd use, because the trials are still 3, right? There's still n equals 3, but the value of r, or the value of x, is going to change. So when x equals 3, it would then be 3c3 for NCR. When x equals 2, it'd be 3c2, x equals 1, 3c1, when x equals 0, it'd be 3c0, 3c0, etc. And we get these different probabilities that should all hopefully add up to 1. Okay, so we'll do an example now. Find the probability of obtaining 3 heads when a coin is tossed 6 times correct to 3 decimal places. Pretty classic question. This is just be simple familiar. So it's only heads or tails, so already we know that it is going to be a Bernoulli sequence. And probability is the same, independent trials, etc. Now, we're going to let success equal heads, and we're going to let x equal the number of heads we're going to observe, where the probability is 0.5, probability of 6 is 0.5, r equals 3, and the number of trials equals 6. So the probability that x equals 3, now we just apply the formula in the formula sheet. And what we get is this combinatorics at the front where n equals 6 and r equals 3. Now, if we go back to our permutation, you could use a calculator, of course, but n equals 6, so 1, 2, 3, 4, 5, 6, 3, 1, 3, and we find that that's equal to 10. And that would just be a scalar multiple of these two values here. And look, at the end, you get 5 over 16, and that's the probability that we would get 3 heads when we toss the coin 6 times. So fairly likely, considering all the outcomes we got right. One thing, see that logic I just used then? That's checking reasonableness. And after you've done a question, you should always look at it and go, okay, is it reasonable? And there's basic levels like, is the probability between 0 and 1? Okay, that means that, yeah, it's probably fairly reasonable. Or if it's crazy high or crazy low, you might go, why is this? Is this reasonable? Okay, so a Bernoulli random variable describes the outcome from a Bernoulli trial. So if x is the number of successes in n number of Bernoulli trials, each with the probability of success of p, that means we've got a binomial probability distribution. So we can actually graph this and, the probability and outcomes of x. So binomial distributions we represent like this. The binomial probability distribution is different for values of n and p. If we change n, if we change p, it's going to affect the value, of p of x equals x that we get. So an example here would be probability of guessing MCQ questions with success rates of 0.2 versus 0.5. So when so this is like the number of outcomes that we get versus the different, probabilities. And the probability of obtaining that number of outcomes successfully guessed is different depending on the probabilities. For example, in the first one, when the probability is only 0.2, so if you're guessing those MCQs, you're only getting four or six right? Between 2 and 6 really. Whereas if your probability of getting it right is 0.5, so it's true false, as you can see, the binomial distribution is centered around 10. The mean is 10. That's the highest point. That's the mean. And it's kind of even as well. I'll note that that's even. And the probability of 0.5 corresponds with 10 there. And, you're probably passing about 50% of the time by guessing if the guess rate was 0.5. But unfortunately for you guys, that's not the case. Okay, so expected value and variance for binomial random variables. So if x is the number of successes in n trials, each with a probability of success p, then the expected value and variance of x are given by these two formulas. And I've forgotten to highlight these. You don't need to remember how to use it, but you can just put it straight get it straight from the data booklet. I will note you do not need to know how to derive these or memorize these. These are not memorized. These are on the data booklet. So if we're talking about a binomial, bi means two, success and failure, Bernoulli trials. These words all interlinked. And that should be your thought pattern. If we're talking about that, you're going to go to the data booklet, you're going to go to binomial random trials, Bernoulli or whatever it is, on the stats page, page 2, I believe, and you're going to apply these formulas. So E of x is the expected value, so the mean of x, n times p. So really simple. It's like in this question here, it's like the mean would be 10 and we have 20 trials. The probability of getting right is 0.5. So 20 times 0.5 is 10. That's the expected value. You can see how this all kind of works out and makes sense, essentially. Then the variance of x, a little bit more complicated, np times 1 take p. Yeah. So you just apply them, and remember, how do we work out standard deviation? If we were given that variance, how do we work out the standard deviation? We square root it. That's the standard deviation. As I said before, something you do have to have memorized. Example. So a test has 50 MCQs, multi-choice questions. Each question has 4 possible answers. A student guesses the answer to all questions. So let x equal the number of correct answers. So success is correct. X is the number of successes. And it is a Bernoulli sequence. That's step 1 we were supposed to do because there's success failure, independent trials, and also its probability is constant. It's not changing, essentially. So how many would be expected to get right? Well, we're just going to apply the formulas that we got from the data booklet. And here, I've applied it here, or I've highlighted it here on the stats page. N times P, 50 times a quarter. Similarly, for variance, we just sub in N and P to that formula. And what we get is 75 over it. And you're thinking, oh, that's more than one. Well, it can be more than one because we're talking about the variance of x now as opposed to the the expected value. Well, I mean, they can all be above 1. If you're talking about probability between 0 and 1. Sorry. Okay, so sometimes we want to find out, sometimes we want to find the sample size. And like I've shown you the basics now, you've now been shown the basics, but sometimes you have to go the other way. Sometimes you're given a probability of something, or they say, try and find the probability of finding this. And then you have to backtrack to find the sample size we need to get that probability to actually work, given the probability, etc., to observe a certain outcome. So an example would be, if we had, how many lotto tickets would we need to buy to ensure a 95% probability of winning? And if you were just given this question, by the way, you would not be able to answer it. That is not something you would have to answer. The reason for that is because, yeah, you're given P of x equals 0.95. However, and you're trying to find N. However, we haven't been given what? We haven't been given R or yeah, well, actually, yeah, we have been given R. We haven't been given the probability of winning on a single lotto ticket because R would equal 1 because we only need to win once. R would be 1 up to N, and N would be equal to, that's what we're trying to find. And then P of x equals R would equal 0.95, as you're going to see here. So, yeah, the information we need is the probability of scoring equals 0.48. And here would be some example. So this is an example question I show you But here is for goals. So before we were talking about lotto tickets, but here we'll talk about goals. So what is the least number of shots that must be played to ensure that the probability of winning at least once is more than 0.95? Or at least twice is more than 0.95. And for question one, this would be how you would work it out. So using our binomial sequences, the probability that we're going to get, the probability is more than 9.5 of getting at least one, well, we would write that like probability of x greater or equal to 1 is greater than 0.95. And as soon as you write that sentence, this question becomes really clear because now we can work it out mathematically. Before it was super vague and, we can't actually work that out. So what I want you to know is if it's binomial, you should always, and we're asking for sample size or probability, etc., always state what you know. State what you know, and eventually it'll click through in your mind. You'll know what to do. And this, in terms of math, sometimes it's not this way, and you can have a fair bit more confusion. But at least here, it's nice and simple in that it kind of links in from one thing to the other. It's very sequential. Hence, you can't skip steps, but you can just work through it, and it does make sense. So it's small logical leaps from next thing to the other. Hence, it's not complex, unfamiliar, really. Okay, when you combine distributions, that's when it becomes complex, unfamiliar, and you'll find complex, unfamiliar questions for that in your textbook. So, right, probability that x is greater or equal to 1, we want to find when that is greater to 0.95. Well, I've skipped a couple of steps here, but essentially, greater or equal to 1 means that it's the inverse of x equals 0. Because we're talking about 1, 2, 3, 4, etc., all the way up to n. So what we're going to do, because it has to be a discrete value, we can't use the greater equal than signs in the actual probability. That's not going to work out. We're not going to be able to get a number. But if we do one take the probability that x equals 0 and we sub it in, so we have p equals 0.448, r equals 0, what we're going to, and then n is what's unknown. If we work that out, what we're going to get ultimately is 1 take 0.52 to the power of n. Then we minus 1 from both sides, get rid of that negative, and what we'll get is 0.052 to the power of n is less than 0.05. And right now this is like, what the heck, this is still confusing. But if we take the natural log of both sides, what we get is a mathematical expression that can actually be simplified. So if we divide out the logs, then what we get is that n, if we work it out properly, we'll get a mathematical result with this, right? We'll be able to use our calculators and work this out. And if it was tech free, we would just leave it as such. You could also, like, I know in year 12, I wasn't using these equality signs like the greater or less than. I was just using equals, and then I would work out in my head, okay, so what's the minimum limit here? And then I would then put the equality in at the end. And that's totally fine. That's all good by me. If you are using equalities, the one thing to look out for is sometimes you've got to flip it. So you'll see in step 2 here, I flipped it, and that's because I've minus 1 from both sides. That's why it's 0.405 on the left. Now, that would mean I've got a negative on both sides, so I divide out the negative. And if you divide by a negative, that means you have to swap both sides. Divide by a multiplier, a negative, it doesn't matter. You have to swap both sides. Okay, part 2. So part 2 was asking, okay, at least twice. So the probability of scoring a goal at least twice being more than 95%. So once again, all we have to do is just set it up as a function. So we're trying to find the probability that x is going to be greater or equal to 2. And that probability is going to be greater than 0.95. Now, another way of writing that is that the probability of x being less than 2 is less than 0.05. Okay. And if the probability of x being less than 2 is less than 0.05, well, what are the two discrete values we have when x is less than 2? Well, it can't be 2. It's just x equals 1 and x equals 0. So what we do is we just add up the probability of x equals 0 and x equals 1. Here I've got the two expressions. This is using the the formula for binomial distribution. I've gone over it before. It is just in your data booklet, so you can just apply this one. Nice and easy. So you sub that in, work out the combinatorics using your calculator, etc. Sub these in, work it out. We get this value of n. Now, this is not solvable, FYI. This, because we got n over here and n here and n here, this is not solvable algebraically, not solvable. You need to use like a weird Gaussian limit. It was like it's essentially obscure maths that isn't algebraically solvable. So what that means is you have to use nsolve. And if you're like, what the heck is nsolve? It basically just automatically solves any expression. It's really good. Use it and abuse it in your exams, methods, specialists, whatever it is. Use it and abuse it. Essentially, it just automatically solves the question. You just type in the expression, and then go like comma, what will you want, and a bound potentially. And this is the calculator I have. But it's probably in a different one for your calculator potentially. So what I want you to do is search up YouTube tutorial for numerical solve. That's what the end solve is, numerical solve. And it'll give you a short YouTube clip. It'll be like a minute long. Just tap through that because it is a life changer. It makes tech active papers actually much easier than tech free because you can skip so many steps. I remember in year 11 we had a tech active question where if you try, like, people spent half an hour trying to solve this question. It was actually unsolvable and it was only worth 1 mark for applying the end-solve function. Like, this is in marking guides. You need to know this. This is really high yield. End-solve. No. Or numerical solve, whatever it is in your calculator. Solve any expression tech-free automatically. And sometimes there's multiple, but you'll see that in a good YouTube video.